Good evening all. Welcome to TCS NQT 2026 coding training day 10. Hope you are all doing well, preparing well for TCS NQT 2026 exam. So audio, is it clear? Am I audible? Yeah, am I audible? Lohit? Okay, thank you. Done. So today we will discuss one more coding question, previous coding question. So let me share. So we will discuss September month exam day 1 slot 1 question. Okay, so this is the question asked in TCS NQT 2025 September month exam. So let us understand the question first, then we will solve it. Now, so the problem statement is given as follows. Joseph is learning digital logic subject, which will be for his next semester. He usually tries to solve unit assignment problems before the lecture. So today he got one tricky question. The problem statement is a positive integer has been given as input. Convert decimal value to binary representation. Toggle all bits of it after the most significant bit, including the most significant bit. So print the positive integer value after toggling all the bits. Now this is the question given. Okay, so ultimately what we need to do in this question. Okay, so it is understood that we need to convert a given decimal value into its binary representation. Okay, but before printing the output, we must toggle all the bits. Okay, so toggle all the bits in the sense we need to invert the bits. Okay, so 0 we need to convert is 1 and 1 we need to convert as a 0. Okay, so that is called toggling. So after toggling, then what is its positive integer value? That value we need to print. This is the given question. Constraints are given n between 1 to n. Okay, so input is like this. 10 is given. This is the integer number given, and the output 5 result again it is an integer. Result you must print as a decimal value, not the binary value. So explanation is given here. Binary representation of 10 is 1010. So after toggling the bits 1010, we'll get a 0101, which represents a 5. So hence the output will be 5. So that's why we got the output as a 5. Now this is the given question. Okay, so input 10 given and 5 should be the output. Okay, so how we get this binary representation? We know how we can convert 10 into binary form. Okay, so by dividing 10 with 2, then all the reminders you should catch. Okay, so 2 5 is 10, then the remainder is 0. Then 2 times 4, then the remainder is 1. then 2 ones 2, then the remainder is 0, and we need to write the binary representation from bottom to top. Okay, so that means 10 in binary is equals to 1010, sorry, 10 in a decimal is equals to 1010 in binary. Okay, all right. So if you know this conversion, dividing with 2 and getting this value, then you can straight away convert this mathematics into program. Okay, so but before this, what is given we need to understand in the question. Okay, so if 10, we get 10 here. Okay, 1010, if we get 1010 here, so what we need to do, we need to toggle all the bits of this binary representation. Okay, so that means if you toggle, what you will get, this 1 becomes a 0, and this 0 becomes a 1, and this 1 becomes a 0, and this 0 becomes a 1. So you are getting 0 1 0 1. It's just like finding the ones complement of this number. So this 0 1 0 1, so what is the value here? It is 1 0 1 we got. Anyhow, this left side 0 is not required. Okay, so it is no value for this 0 here. Okay, so then this is binary representation. So how do you get its decimal representation? Multiply each bit with the powers of 2 here. Okay, so if you multiply with powers of 2, 1 multiplied with 2 power 2 plus 0 multiplied with 2 power 1 plus 1 multiplied with 2 power 2. Okay, so this 2 power 4 is 2 power 2 is 4, 4 ones are 4, plus this is 0, plus this is 1, so then the answer is 5. So you should know this mathematics. If you know this mathematics, then only you can write program for this. Got it? Okay, so let us write the program directly. Binary conversion we will perform. Okay, right? So for that we write the program. So what is our main code? So main code, you need to read an integer value here. Okay, so integer value int input. Got it? Okay, so I'll write a bit below so that we can write the function, or directly you can write the main code itself. Okay, so directly you can print the result. Okay, so directly I'm writing inside the main itself. So int, then read the number n value. So first n value you will get here. Okay, so your n value is 10 here. Now you got the n value. Okay, so ultimately you have to store the result here. Okay, so binary representation you require, no? So initially we store we take a variable binary and assume it as a 0. Okay, so binary representation of this one we need to store in the variable called as binary. I'm taking it as a 0. Okay, right. Now what else you require? First you need to divide this 10 with 2. Yes or no? 10 you need to divide with 2. Okay, so that means you need to obtain the remainder here. Okay, so the remainder you should catch that remainder. So if you divide, then you are getting the remainder. In ordinary division, how you do this? 2 5s 10. Okay, so remainder 0 here. Then this remainder 0 you need to catch this remainder. So, okay, so for storing that remainder, we will take a variable, or variable not required, directly you can use that variable. Okay, now so what is happening? Okay, so this division, how long you should perform this division with 2? Okay, so just if you observe here, So what is happening first, 10 becoming 5 here. Again, you are dividing 5 with a 2. Okay, so 2 times remainder 1. Now your n value becomes 2 here. Okay, so then you are dividing with 2, 1 times remainder 0, then it becomes 1 here. N value reduced to 1 here. Okay, so again you divide with the 2, so 0 times, then it becomes a remainder is 1 here. So what is happening here? Initially this is your n value, afterwards your n value reduced to 5. Okay, so next what you are doing, you are dividing 5 with a 2. Okay, so then you are getting this remainder, you are taking this remainder. Okay, so now this becomes your n, 5. Next time 2 becomes your n, next time 1 becomes your n, next time 0 becomes your n. So when it becomes 0, you should stop. Okay, so this becomes the stopping criteria. That means as long as n is not equal to 0, you repeat the division. Okay, so for that what we do is we'll use a while loop here. Okay, so I write the while loop here. Direct mathematics I am converting into program instructions. Look at here. Okay, so while n not equals to 0, there are functions available, but if you don't know any function, okay, so this is how you can write the code. Okay, so mathematics, you know mathematics, but that mathematics now you can convert into program instructions, then you are done, that's it. Okay, so while n not equals to 0, okay, so I am writing all the values here. N value is initially 10. Okay, what we need to do, we need to divide n with 2 and get the remainder. So n mod 2 I'll write, and I'll store this variable in a variable called as a remainder. Okay, so what I get in remainder I get as a 0. Okay, so this 0 I need to store. Okay, so how I need to store the values, reminders, I should store the reminders from bottom to top I should get. Okay, so that means 1010 I should get. Okay, or what I do is I take a different number so that you can understand easily. Say for example n value I take it as a 11 I take. Okay, so 11 if you divide, now you can just see here. So 2 5's remainder 1 I get here. Okay, so 2 2's remainder 1 I get here. Okay, then 2 1's remainder 0, then 2 zeros remainder 1 here. Okay, so what is the value? This is the value I am getting. Okay, so it is 1011 I am getting now. So this first one I got, this first one I got here. Okay, so that I stored in a reminder. So this I need to add to the binary variable. Okay, so then what I do, I add it to binary. Now I say binary plus is equals to reminder. I say binary plus is equals to reminder. Okay, so binary previously it is 0 0 plus 1 now. Okay, so sorry, now we consider this binary value. Okay, 1011 I am considering this 11. Okay, so our input is 11 now. Afterwards we'll test with 10. Okay, so we are working with 11, n value is 11. Okay, so this first one we got after first division. Okay, so remainder is 1 here. This one I am adding to binary here. Okay, so previously binary is 0. Okay, so 0 plus 1 is 1 here. Okay, so it becomes 1, it becomes 1. So that means the first digit I stored in a binary variable. Okay, so what else I required? Once I got this, okay, so I need to get reduce the n value to 5 here. Okay, so how I can reduce the n value to 5 here? So where I am getting that 5? I am getting the 5 here. Okay, so that means if you divide 11 with 2, 2 5 is 10, remainder is 1. So this 5 I am getting in the quotient. Okay, so that's why what I need to do, I need to reduce the n value. So n here integer division or floor division I need to perform. Okay, if I use single slash it becomes 2.5. Okay, so only 5 I should get, sorry, 5.5 I get. Okay, but here I require only 5 no, so integer division I need to perform. So n slash is equals to, okay, so then you say 2. What does it means? It is nothing but n is equal to n slash 2. This is nothing but n slash 2. Okay, so when you divide n with 2, the quotient it returns, that quotient you are catching in n. That means you are reducing the n to 5. N value becomes 5 here. Okay, so then again it goes up, the loop repeats. Okay, so 5 not equals to 0. Yes, 5 not equals to 0. Yes, now you divide 5 with 2. This is what you are doing here. Okay, so remainder is n mod 2, 5 mod 2. So divide 5 with 2, 2 2's, then the remainder is 1. Okay, so you will get the remainder as a 1. Now what happens, just look at here. So if you write this instruction, binary plus is equal to remainder. Okay, so it is nothing but binary remainder you are adding to binary. Okay, so remainder is 1 here, binary value previous value is 1. So if you add 1 plus 1, you get the result as a 2. Okay, but you should get the result as a 1 1. Okay, so ultimately what you require in this 1 1, you should get the result as a 1 1. Okay, so that means in this binary representation 1 0 1 1, now you understand clearly here. Okay, so this 1 we got here. Okay, so if you take their place values, okay, so this is in a units place or ones place, this is in a tens place. Okay, so this is in hundreds place, and this is in a thousands place. Okay, so if you add 1 plus 1, it is becoming 2. Okay, but it should become 11 here, it should become a 11 here, it should become 11 here. Okay, so that means this one place value you should obtain. Okay, so since 1 is in a tens place, it should become 10, not 1. Okay, so this value of this one should become 1 here. Okay, so then you will get this 1 1. Otherwise what happens, you get the numbers in reverse order if you just add them, or you will get a decimal value which is not at all useful to us. Okay, so this one is in tens place now, that means we need to keep track of place values. Okay, so place values we should keep track. So for that what I do is I take a variable called as a place value, and initially I take the place value. Place value starts with ones, no, units place, no. So we take the first place value as a 1. Okay, so units place I am taking as a 1. Okay, now what we need to do, just look at here again, we'll start from the beginning here. Okay, so when you get this first one, it should be in units place, no, it should be in units place. Okay, so a number present in units place, okay, so its value should become here number into 1. Okay, so here 1 into 1 means its value should be 1 here. Okay, right. So now again trace the program here. While n not equals to 0, n value initially is 11 here. Okay, so 11 not equals to 0. Yes, reminder 11 mod 2. When you do this 11 mod 2, see here 1 you are getting here. Okay, so this first units digit 1 you are getting. Okay, so when you get this 1 here, okay, so you should add it to units place. You should add it to units place. That means this statement you should remove now. This statement you should remove now. Okay, so then your binary value must be equals to, okay, so what it should be, it should be place value multiplied by remainder, place value multiplied by remainder plus add it to previous value of the binary, previous value of the binary. Okay, right. So now you can see place value is 1 into remainder is 1. 1 into 1 is 1. 1 plus initially binary value is 0. So 1 plus 0 is 1. So that means you get this first one here. Okay, so in 1 0 1 1, this 1 you are getting. So binary variable value becomes a 1 here. Okay, so now you are reducing the n value to 2. Okay, but before you reduce the n value to 2, what you need to do, when you obtain the next remainder, that means when you get this next digit, its place value should be tens. Okay, units tens, its place value is tens. So that means you need to increment the place value. Okay, so your place value should be every time multiply the place value with 10. Okay, so every time it increases by 10 times. So place value is equal to place value into 10. Okay, so now your place value becomes a 10 here. Place value becomes a 10 here. Okay, so now reduce the n value to 2. Reduce the n value to 2. And reduce the n value to next number 5. Divide with a 2. So you will get n value as a 5 here. Okay, so your n value now becomes a 5. So again go up. Okay, what happens we'll see here. Okay, so look at it. So we'll go up. N value is now 5. 5 not equals to 0. Yes, remainder n mod 2. Okay, so divide 5 with 2, you get the remainder as 1. So that 1 you are storing here. Okay, now look at this statement. What happens? So this 1 we got in tens place 1. Yes or no? Tens place 1 we got here. Okay, so now we'll see here. So place value into remainder. Okay, place value into remainder. Place value is 10. 10 into remainder is 1. 10 into 1 is 1. 10 multiplied by 1 is 1. 10. 10 plus binary value, previous value of binary. So 10 plus 1 becomes a 11. Okay, so that 11 we are storing back in binary. That means your binary value becomes a 1 1. Okay, so that indicates we obtained these two digits. We obtained these two digits. Now we are working for the next digit. Okay, which is in hundreds place. That's why I am incrementing the place value by 10 times. Okay, so place value into 10. 10 into 10, it becomes a 100. Next digit place value, hundreds place. Okay, so then reduce n by dividing with 2. 5 means then you get the next n value as a 2 here. N value is reduced to 2 here. Again go up. What happens we'll see here. Again go up. 2 not equals to 0. Yes, remainder is equal to, when you divide 2 with 2. Okay, so what is the remainder you get? You get the remainder as a 0. Okay, so divide 2 with 2. 2 ones, remainder is 0 you are getting here. Okay, so your remainder becomes a 0 here. Okay, right. So now look at this statement. Next statement, what happens? Look at this. Binary is equal to place value into remainder. Place value is 100 into remainder is 0. Okay, so 100 plus into 0 is 0 here, plus binary. Okay, so 0 plus 11 becomes a 11. Okay, so that means we obtained this value. We obtained this value 0 1 1. 11 is equivalent to 0 1 1 only. Equivalent to 0 1 1 only. Okay, so it is assumed there is a 0 preceding 11. Got it? Okay, so then now we need to work for the next digit. That means you need to increment the place value by 10. Okay, so place value into 10. 100 into 10, it becomes a 1000. Next digit is in thousands place. Then reduce n. So divide n with 2. What is the quotient you are getting? 2 you are getting. Sorry, 1 you are getting quotient. Okay, so this quotient, that means n value now becomes a 1 here. Okay, so again go up. Again go up. So 1 not equals to 0. Yes, divide 1 with a 2. Okay, so this last division. So when you divide, what you are getting? Remainder as a 1 you are getting here. Okay, so that means if you divide 1 with a 2 zeros, 0 you get, the remainder you get as a 1 here. Okay, so remainder is 1 in this case. So you get the remainder as a 1. So remainder value is 1 here. Okay, right. So now look at this statement here. Binary is equal to place value into remainder. Place value is 1000 into 1. So it is 1000 plus binary. So 1000 plus 11 is 1011. So your binary becomes a 1011. Okay, so it is 1011. It is nothing but 1011. This value we obtained. 1011 we obtained, which is the binary representation of 11. Okay, so then increment the place value multiplied by 10. 10 place value becomes 10,000 here. Now reduce n value. Okay, so if you reduce n value, what is the quotient you are getting here? 0 you are getting. That means your n now becomes a 0 here. Okay, so when you go up, what happens? The condition becomes a false. N not equals to 0. 0 not equals to 0. False. Okay, so this loop Once you come out from the loop, it indicates that you have obtained the binary representation for the given number. Got it? Okay, so we obtained the binary representation for the given number 1011 we obtained. Okay, now what we need to do? We need to toggle these bits. Okay, so if you toggle these bits, what is the new number you will get? 0100 you get. Okay, so this 0100 you get, and you need to multiply these with the place values. Okay, multiply with the powers of 2 powers of 0, 2 power of 1, 2 power of 2. Okay, so generally in binary representation, for example, if the bits are like this 1011, okay, so this is bit, we call it as 0th bit. Okay, so this bit we call it as first bit. Position, bit position will start with 0, 0th bit, 1 bit, first bit, this is second bit position, this is third bit position. The bit positions we give from 0 onwards. Okay, so that's why, so how you will get the result here? You multiply with the powers of bit position here, 2 power 0, this is first bit position is 0, 2 power 0, next bit 1 position 1, 2 power 1, next bit position 2, 2 power 2. You are multiplying with the powers of bit position with that value. Okay, now do we really require this binary conversion? After binary conversion, this binary representation after toggling the bits? No, we don't require. After toggling, what else we require directly? If you multiply with the powers of 2, then that result we required. Okay, so this is the binary representation after toggling the bits. Okay, now directly what we required? We require the answer here. Okay, so that means 1 multiplied by 2 power 2, 1 multiplied by 2 power 2. Okay, so remaining all are zeros only. Okay, so that means 1 multiplied by 2 power 2, 4 into 1, 4, then the answer is 4. This 4 only we required. Okay, so what we do is, if you observe this binary representation, okay, as you are getting the binary representation, only zeros in the actual binary becomes 1. Only zeros in the actual binary representation becomes 1 in the toggled representation. Okay, in the toggled binary form. Okay, so that means if you just check that while getting this binary representation, if the bit is 0, toggle that bit and just multiply it with the bit position and go on add it to a sum here or result, then directly you get the result. Okay, so I'll take one more example and hope you will understand clearly. For example, if this is our binary representation, okay, so 101010, just assume. Now if you toggle these bits, okay, so if you toggle these bits, what you will get here? 010101 you get. Okay, so what is happening in the original binary representation? The actual zeros only becoming ones. We required only these 1 positions only, because anyhow ones becoming 0. Okay, so they don't add to the actual result. So these 1 positions we should keep track. Okay, so that means while we know how to get these binary bits here. Okay, while getting the binary bits, if your bit is 0, then immediately you toggle that bit. Okay, and multiply with the powers of a bit position. You take a variable called as a bit position, and initially bit position starts with a 0. Okay, so for each bit, now you increment this bit position. Okay, so initial first bit, if it is 0, then toggle it as 1. Okay, so then directly multiply with the 2 power 0. Okay, so it becomes 1 into 2 power 0. You add this to result. I am adding this to result. Okay, so then your result 2 power 0 is 1, 1 into 1, 1. So your result becomes 1. So when you get the next bit, okay, so you increment the bit position becomes 1 because this is bit 1 you are trying. So it is 1, just leave it. Okay, so then get the next bit, it is 0. Okay, so that means next bit position is 2 here. So check here, it is 0, then toggle it and multiply it with a bit position. Okay, 2 power of bit position. Now see here. Okay, so then what it happens, 1 multiplied by 2 power of bit position is 2. Okay, so 2 2s are 4, 4 ones 4, 4 plus previous value 1 here. Okay, so 4 plus 1 is 5, then your result becomes 5. Okay, so then increment bit position becomes 3 here, 1. Okay, so leave it. Increment bit position becomes 4, 0. Okay, so then toggle it, it becomes 1, multiply with 2 power of a bit position. So 2 power 4 is 16. So 16 plus 5 here. Okay, so 16 plus 5 is 21. So next bit is 1, just leave it. That's it. Okay, so that means as we are getting the binary representation, directly you are toggling the bits and getting the result. That's it. This is your result. It is 2 power 0, 2 power 1, 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 16. 16 plus this is 4. 16 plus 4 is 20 plus 1 is 21. 21 you are getting. So that means for this binary representation, directly you are getting the result. Okay, so for our number also we get the result. Okay, so now I am generating these bits, binary bits here. Understand this. As I am generating the binary bits, so initially I take the bit position. I take the bit position starting from 0. Okay, so 0th bit I am keeping track. Initially result I take as a 0. Okay, so then this bit position 1, I just leave it. I go to the next bit. Okay, so before I go, I increment this bit position. Now I generate this 1, then I check, is it 0? No, just leave it. So increment the bit position, it becomes 2. Okay, so generate the next bit 0, is it 0? Yes. Okay, so then toggle it and it becomes 1 and multiply this with a 2 power of bit position. 2 power of bit position is 2. Okay, so this becomes 4. Add this to result. So now your result becomes 4. So then increment the bit position 3. Then get the next bit 1. Leave it. That's it. Over. Okay, so that means from n, as you generate this binary representation, you are also generating the result. Finally, if you print a result, that is nothing but the final decimal value after toggling the binary representation of a given number. Okay, so let us work out for a 10. Okay, so if it is the given value is 10. Okay, so what is its binary representation? 1010, no? Right, so now initially I start with bit position. I start with bit position 0. Okay, so that means I am generating this bit. Now I check, is it 0? Yes. Okay, so result I am taking as 0 initially. Okay, so is it 0? Yes. Toggle it and multiply with 2 power of bit position. Bit position is 0. 2 power 0. 0 is 1 into 1, 1. Add it to result. Now your result becomes 1. Okay, so then increment bit position becomes 1. Now generate this bit. It is 1 here. Just leave it. Okay, so increment the bit position becomes 2. Then generate this and check it, is it 0? Yes. Okay, so toggle it and multiply with 2 power of bit position. 2 power of bit position is 2. 4 multiplied by 1, 4. 4 plus 1 is 5. So your result becomes 5 here. Okay, now increment the bit position, then generate this bit, it is 1, just leave it. Over. Okay, so from the problem statement you need to understand that. Okay, so from this it is not required to generate this toggled result. Okay, so directly you require only this decimal representation for that toggled representation, decimal value for the toggled representation. No need to generate this toggled representation. Okay, so while generating this binary representation you can obtain this result. That's how you should improvise your code. Got it? So now we'll add the same mathematics into our code. We'll add the same mathematics into our code. So this logic I am teaching for those who don't know about the functions. What are the functions available for uh, conversion into binary form, then toggling into. Okay, so you know only mathematics, decimal to binary conversion, you know. Okay, so then the same logic you are converting into programming instructions. If you know functions, it's well and good. You can use functions and directly you can get the solution. Okay, but remembering all the functions is difficult. Sometimes we forget the names of the functions. We do not know whether it works properly or not. Okay, so in such case, you can directly apply your problem solving skill and generate this kind of code here. Okay, so no issue. It is just a order of, because your n value is between 1 to 100 only. Okay, so this works fine. This code works fine. Okay, all right. Now whatever we said, that we'll convert into program instructions. Okay, so for this what we required one more variable called as a bit position. So I am taking a variable called as a bit position, and initially I take it as a 0 here. Okay, similarly we require another variable called as a result, then initially I take the result as a 0. Okay, right. So now we'll generate the code. Okay, so let me take another color pen so that you can understand the steps. Now we'll start with the n value is equal to 11. N value is equal to 11. Okay, so what we are doing, this is our actual binary representation. We are trying to generate this binary representation. At the same time we toggle and we add it to the result directly. Okay, so which bits only we required in the binary generation? Only the bit which is 0 we required, because these zeros ultimately adds to the result. Okay, once they are not going to add, so that's why as we generate each bit we check whether it is 0 or not. If it is 0, then we toggle it and multiply with 2 powers of bit position. This is the logic. Got it? Okay, right. Now see here, n not equals to 0, n value is 11 here. So 11 not equals to 0. Yes, you are generating the remainder. Okay, so this first division I am doing here. Just look at this first division I am doing here. Okay, so I remove all the variable values from here so that you can easily identify the values. Okay, so initially binary value is 0. Okay, so place value is initially 1. Okay, so then result is equal to 0 here. Okay, right. So now see here, reminder, you got the reminder, this first division reminder you got as a 1 here. 1 we got. Okay, so now we are trying to get this binary representation. Okay, so this representation, so it is place value into reminder. Place value is 1 into reminder, 1 into 1, 1 plus binary 0. Okay, so then binary value will become 1 here. It becomes a 1 here. Okay, so then you are incrementing the place value. You are incrementing the place value, multiplying 10 times you are incrementing. Okay, multiplying the place value by 10. Okay, so then reducing the n value to next number. Okay, so n value now becomes a 5 here. N value becomes a 5 here. Okay, so before you go to the top of the loop here. Okay, so now you check, you got the bit in variable called as a reminder. In reminder you got this first bit. Okay, so its position is 0, bit 0, bit 0 you got. Okay, so now you test it whether it is bit 0 or not. Okay, so if your reminder is equals to 0, if your reminder is equals to 0, okay, so what we need to do, we need to multiply this with place value. We need to multiply this with a place value. That is what we said here. Okay, so in this case what happens, we will see here. So remainder is 1. In this case 1 is equal to 0, no. Okay, then what we need to do, we need to increment the bit position. Okay, so this true condition we will write afterwards. I just write as a pass here. So then I am incrementing the bit position. Okay, so bit position, because next bit I am trying to generate now, so I am incrementing the bit position. So 0 plus 1, it becomes a 1. So your bit position, where is the variable? I write the bit position variable here. Now bit position becomes a 1. Okay, so now it goes to the top of the loop here. Okay, so now see here, now n value is 5 here. 5 not equals to 0, yes, remainder. Okay, so this one, when you divide 5, remainder you are getting as a 1 here. Okay, so that will be stored in a remainder. Remainder now contains a 1 here. So then binary is equal to place value into remainder. Okay, so 10 into 1, 10 plus binary plus 1. So 10 plus 1, it becomes a 11. Okay, so your binary value now becomes a 11. That means the first 2 bits you obtained here. Okay, now incrementing the place value by 10 times, place value multiplied by 10. Okay, so previously it is incremented low, now it becomes a 100 here. Okay, so then n value reduce, n value now becomes a 2 here. Okay, so now you check here, if remainder is equal to 0, remainder, what is the remainder we got? See here, if you toggle these two numbers become 0, they don't add to the result. Okay, so that's why we have not yet encountered a 0. Then this I just pass here, then I increment the bit position. Okay, so now bit position becomes a 2 here. Okay, so bit 2, I am trying to generate a bit at position 2. Okay, so I go up again, go to the top of the loop here. So 2, n value is now 2. 2 not equals to 0, yes, remainder. Okay, so this division, so remainder 0 I'll get here. Okay, so now we get the remainder value as a 0 here. Okay, now see what happens. So then binary is equal to place value into remainder. Place value is 100. 100 into 0 is 0 here, plus binary 11. 0 plus 11 is 11 only. Okay, so nothing but it is 0 1 1 you obtained here. Okay, then place value you are incrementing by 10 times, so place value becomes a 1000 here. Your place value becomes 1000. Then you are reducing the n value by 2. Okay, so your n value now becomes a 1 here, quotient here. Okay, so here the quotient is 1 now, n value reduced to 1. Now look at this statement here. Okay, so remainder is equal to 0. What is remainder? 0. Okay, that means we obtained this bit here. Okay, so remainder 0. Yes, now what we need to do, just look at here. So let me erase this pass. Now we need to write the actual code here. Right, so remainder 0 we got here. So what you need to do, you need to multiply, toggle it and multiply with the 2 to the power of bit position. Okay, so now what I am doing is I am multiplying with bit position. Okay, so when if I toggle, it becomes 1 here. Okay, so 1 multiplied by 2 to the power of 2 to the power of bit position. 2 to the power of bit position. Okay, so the equation in mathematics for this is, it is nothing but like this. Okay, so bit position is 2 now. 1 into 2 to the power of bit position value. What is bit position value here? 2. Just look at here, bit position value is 2 here. Okay, so it is nothing but 1 multiplied by 2 to the power of 2. Double star I used exponential operator here. Okay, so it becomes a 4. Okay, so this 4 I need to add to the result here. Okay, so what I should write here, so I should write here. Okay, so result plus is equal to result plus is equal to. Okay, so this right hand side is calculated and that will be added to result. Okay, so now result becomes 4 plus 0. Okay, so your result now becomes 4. your result becomes a 4. Okay, so then this is inside the if statement. Okay, so I just move this if little bit here, because indentation while typing will follow that indentation. Okay, so this entire thing is in if. After coming out from the if, this is the bit position value. Okay, so this we are writing after coming out from the if statement. So I write just don't get confused. Okay, so it is now I'm incrementing the bit position after coming out from the if statement. Bit position plus is equals to 1. Okay, so bit position now becomes a 3 here. Okay, so that means this bit position 3, third bit we are trying to generate here. Okay, so again you go up the loop, then check the condition 1 not equals to 0. Yes, reminder. Now this division we are doing. What is the remainder? You get 1 here. Okay, so remainder 1. So place value into remainder. So place value is 1000. 1000 plus 1. Remainder value is 1 this time. Remainder value 1. Let me replace this 1. Okay, so now it is 1000 play into 1. 1000 plus a binary value. So 1000 plus binary value is 11. Now it becomes a 1011. Okay, so if you erase this, it becomes 1011. Now this is 1011. Got it? So then what you are doing, you are incrementing the place value, multiplying by 10. 10,000 it becomes, reducing the n value. Now see, if you reduce, what is the quotient you are getting? 0. So that means finally your n value becomes a 0 here. Okay, so then you are checking remainder is equal to 0. Remainder 0, no, it is not 0. Okay, so this is not executed. Incrementing the bit position now becomes 4. When you go up the loop, now the condition becomes false. Okay, so n not equals to 0, 0 not equal to 0, false. That's it. Okay, so now you obtained the result after toggling. This is the binary representation. After toggling it, okay, then what is its equivalent to decimal representation? 4 you are getting, which is obtained directly in a variable called as result. So after coming out from the loop, okay, so directly you print the result here. That's it. Your result will be printed. So this way you can convert the mathematics into programming instructions. Okay, so now you can work for other numbers also. It works fine. Okay, so let us quickly type the code and let us execute the code. Okay, so we'll go to online compiler. Yeah, this is our online compiler. Okay, so let me remove everything. So I type the code here. First n value we require now. So int of input. Then what variables required? Bit position you need to store. Bit position, initialize it to 0. Then result you required. Result initialize it to 0. Okay. Then place value you required. Initialize it to 1. Okay. Just I'll show the code here because it is moving up the screen. What else? Place value we required. Okay, so what else variables we binary? Okay, so place value is 1 no. Then we required binary number. So initially we store the binary as a 0. Okay. Right, so these 4 variables we required initially. Now run the loop here. So while n not equals to 0. While n not equals to 0, get the remainder first immediately. Remainder is equal to n mod 2. in mod 2. Okay, so then what you need to do, you need to add the remainder to binary. Okay, so binary you can write like this, plus equals to, or you write like this, binary is equal to place value multiplied by remainder plus binary. Okay, so afterwards we'll add shortcuts to that. Then what you need to do, then you increment the place value, place value, place value multiplied by 10, increment the place value by 10 times. Okay, so then what else you require, you reduce the n value. Okay, so n double slash equals to 2, divide n with 2, get the quotient you are getting. Okay, now you have remainder with you. Now you check whether your remainder is equals to 0. Okay, so if your remainder is equal to 0, then you need to toggle and add it to the result. No, so what you need to do, you need to add it to the result plus is equal to. Okay, so 1 multiplied by, when you toggle you will get 1. Okay, so directly I'm taking it as 1. Okay, so 1 multiplied by 2 to the power of bit position. So 2 to the power of bit position, bit position I am getting. Okay, so after coming out from the if, increment the bit position plus equals to 1 you say, that's it. Okay, so this loop repeats, and once you come out from the loop, now you can print the result. Okay, so let us run the code. Now you can enter the value 10. Now you can see 5. Okay, as per our this thing. Now if you look at the problem statement, see here. Okay, so for 10 the output is 5. For 10 the output is 5. Okay, so we also worked out one more example. That is 11 also we worked out now, so that also we will give as input and we will just check out. Now let us run the code once again. Now this time I give the input as a 11. Okay, so now you can see it is not direct binary conversion of 11. Okay, so result is not the direct binary conversion. Okay, so it is nothing but toggling the binary conversion. Okay, so then you are getting this result 4 you are getting as per the problem definition. Okay, so you can work out different numbers and you can check. So 25, see here you are getting as a 6. You can manually work out this and test your results. Okay, so your manual result and program result both should match. If any deviation in the input and output, you can just comment in the comment section of this video. If there is any deviation for any number, then we can look back the code. So this code works fine. I don't think it fails. Okay, so friends, this is the logic I developed for those students who don't know what are the functions available. Okay, so for getting a binary representation directly. Okay, so if you are good at mathematics, good in problem solving, okay, so direct to mathematics you can convert into the program instructions like this. Now, okay, so with the functions, how we can solve this problem easily. Okay, so because I need to introduce those functions also, and it may help you in the examination. Okay, so if you convert a given decimal number into binary by using a bin function, okay, so you will get its 32-bit or 62-bit representation. That means all 32-bit, 64-bit representation you will get. Okay, but we want only the number. For example, 5, the actual bits we want. 5 binary representation is 101. Not all 32 bits we required. Okay, so 10 binary representation is 1010. Only these 4 bits we required. The actual binary representation of the numbers, that means the actual binary bits only we required. Okay, so for that we have a function called as a bit length. In binary we have a function called as a bit length. Okay, so if you give something like n value as a 5, okay, so n dot bit length, if you call this function, then it gives the actual binary digits required for its representation. Okay, so now we can use this bit length function, and how it can be used, we'll see. And another important uh, observation is, if the given number n is in binary, okay, 1010, okay, 1010, then what you are getting, you are getting the result. So after toggling, then the result what you are getting, see, the toggled bit is 0 1 0 1 you are getting. Okay, so which is equals to 5, which is equals to 5 you are getting here. Okay, so this you can obtain directly by like this. So 1010, if you perform exclusive or with this mask, okay, so this is called as a mask. You generate a mask containing all 4 ones. You will get a number of bits by using this bit length function. Okay, so n value is equal to 10 means n requires only 4 binary bits. Okay, so bit length means 4 bits length you will get. Okay, so you generate a mask containing all ones. Okay, so now you perform a, assume that this is n value and this is your variable called as a mask. Okay, so now you perform exclusive or between these two, n exclusive or mask, what you will get, just see here. Okay, so different you will get 1, same 0, different get 1, same 0, which is nothing but our result. If you can generate this mask containing all ones and perform exclusive or, okay, so it is just like a internal python will do this. Okay, but externally what we do, we just write n is equal to 10 and we generate the mask value. Okay, so what is this mask value? It is 2 power 0, 2 power 1, 2 power 2, 2 power 3. Okay, all 4 ones means it is nothing but 15. Okay, so you are just like a performing a exclusive or 15 exclusive or 10, which is equals to 5. That's it. At high level we are doing this, but internally it is performing a binary exclusive or operation like this. Internally it is getting. Okay, so the result directly you can obtain like this at higher level. Okay, so this is all we need to concentrate in the program. Internal things Python compiler will take care. Got it. Okay, so let us write the code, improvise the code by using this bit length function. Okay, so first we read the code directly. Shall I type the code? It is better, I think. Yeah, screen got struck. Hope now screen is visible. Got it. Okay, so here we have a method called as a bit length. In Python, we have a method called as a bit length, which gives the actual number of bits required to represent a decimal number. Okay, for example, n value is equal to 5. If you give 5 in binary, can be represented as 101. So then when you ask bit length of 5, then it gives as a 3. It gives as a 3. Okay, so if n value is 10, so its binary representation is 1010. It requires only 4 bits. Okay, so if you ask a bit length of 10, then it gives the result as a 4. Okay, so why we require this actual number of bits? Because we can use a XOR property here. Okay, so if your n value is in binary 1010, okay, and if you can generate a mask of a 4-bit length, mask containing all ones, okay, then if you perform XOR between these two, n and your mask, okay, so what the result you will get, just see here, 0 and 0 XOR 1, different, no, so it is 1. If the bits are same, result is 0, different, it is 1, bits are same, result is 0. Now this is what the 5, which is nothing but our result. So we can use this XOR property and directly we can get the result here. No need to write any loop or nothing. Just exclusive or operator we can use. Okay, so what else? So what we do here? We try to generate this mask. What is the value of this mask? It is nothing but 15. Okay, so 4 bits you want to generate a mask containing all 4 ones. All 4 ones. How you can generate? How you can generate? It is nothing but 2 power 4. This mask is nothing but 2 power 4 minus 1. 2 power 4 is 16 minus 1. It is 15. That means in binary it contains all ones. In binary it contains all ones. Okay. But how you can generate a binary containing all ones, 4 ones here? 4-bit binary number, how you can generate? Now what you can do is you can use the left shift operator. Okay, so if you can move 1 towards left by 4-bit positions, 4-bit positions, what you will get here? That means assume that 1 is represented as a 8-bit like this, 0 0 0 0 0 0 0 1. It is represented in 8-bit like this. Okay, so if you move 1 towards left 4-bit position, so that means 1, this is 2, this is 3, this is 4 bits. Okay, so if you move 4 bits here, then 1 comes here. Okay, so then it becomes 0 0 0 1, then followed by 0 0 0 0. Okay, so in decimal it is nothing but 16. In decimal it is nothing but 16. 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. 2 power 4 is nothing but 16. Okay, so this is what we have generated. 2 power 4 we have generated. Then minus 1 you say, 15 you will get. Okay, so if you subtract 1 from this, then you will get 15. 15 with all 4 ones. 15 is represented as a 111 using the 4 bits. Okay, so this mask you can generate like this by using the left shift operator. So 1 left shift by 4, then you say minus 1, which is equal to this one. Okay, so these properties we'll use and we'll write the code. Okay, directly I type the code. So we'll go back to online compiler. Now I keep this everything in comments. Okay, so previous code I keep in comments, right? So now we write the actual code by using bit length method and function and left shift operator and exclusive OR operator. Okay, so what we do is directly now you can define a function here. I just keep this code down. Okay, I move it to down. Entire code in comments. Okay, so now I read the n value. Okay, so directly now I can just define a function. Okay, so it's just like a toggle something like binary or some. Okay, then pass this n value, so it toggles and returns the result value. Okay, so this I'll define here. I define the function here. So define a toggle binary, then pass n value as argument here. Okay, so here if n value is equals to 0, that means actually this is not required because in problem statement constraints n is between 1 and 0. 1 to it is between 1 to 100 he has given. No? Okay, so always the test cases contains the n values from 1 to 100 only. Okay, so sometimes if it is 0 given, okay, so you should handle the result like this. If n value is 0, okay, so directly you return the result as a 1 because 0 toggled it gives the result as a 1. Okay, so otherwise what you need to do, you generate the mask. Okay, so now what you do is you generate the mask. Okay, so for that first what you need to do, you need to know the actual number of bits in n. Okay, so n dot bit length. So use the method function called as a n dot bit length. It gives the actual number of bits required for represent this n. Okay, so 4 it gives 4. Okay, so this now you left shift 1 by these number of bits. Left shift 1 by these many bits. Okay, so then you will get this and finally subtract 1 from that. Okay, so then you will get all ones representation for this and you call it as a mask. You give a variable name called as a something like a mask. Okay, so you'll get our four ones you will get here. Okay, so once you get our 4 ones here, directly you can perform a exclusive OR with the mask. N exclusive OR with the mask. Okay, so then it gives the result that you store in the result or directly you are returning the result. No, so you return the result as this. That's it. This is your code. Simple 4 lines of code. Okay, so create the mask. You will get a actual bit length. Okay, so left shift 1 by these many bits and finally subtract 1. You will get all ones here. That is your mask. Now perform exclusive OR with the mask. You will get the result. Okay, so now we run the code. Okay, so here syntax error bit position. Okay, so I think this will here one more. This one, right? Okay, right. So again run the code. Syntax error n mask return spelling I have written wrong. Okay, so now run the code. Okay, so 10 will give. Now you can see none it is printing. Why? Yeah, because everything I included inside the if statement. No? Okay, this. So if n is equal to 0, only this one should be executed. Otherwise, it should come here. So I should follow this indentation here. I should come here. Okay, so Run the code. Now execute the code. Enter the input. Now you can see the result as a 2 you are getting. Okay, so why it is 2? 5 we should get, no? If n value is 10, n value is 10. So what is happening here? So why we are getting 2? Because this arithmetic operator has a higher precedence than a bitwise operators. Okay, so that's why the n dot bit length generates 4. 4 minus 1, 3 is calculated first. Then 1 is left shifted by only 3 bits. Okay, so we want this left shift to be calculated first. So that's why we enclose this in parenthesis. Okay, so then what happens? Left shift operator has less precedence compared to arithmetic operator minus. Okay, so you enclose this in parenthesis. Left shift will be carried out first, then it generates 16. 16 minus 1 is 15. That 15 becomes your mask. Okay, so now run the code again. So this time I enter 10. Now you can see 5 generate. Result is 5. Okay, so these things you should understand. Okay, so if you miss this parenthesis here, you never know where the mistake is. That means the precedence table you should remember very well. Now run the code once again. Let us check for 11. It is giving the result as 4. Again run the code. 25. Now see 6 we are getting as per our previous result. Same 6. There also we got 6 with previous code. Here also we are getting a 6. Okay, so this way you simple mathematics you convert into programming instructions, and you can generate the code by using this piece of code if you don't know the functions available. Okay, so if you know the functions, then you can use the function here, bit length function you can use. Okay, so with binary function you want to perform, just check out how you can do different functions. Different ways of finding the solution is possible. Okay, but this is the best solution. Instead of using binary, this is the best solution. You can use this bit length because the actual number of bits only we required for representing a number. Remaining we don't require. Okay, so I suggest to use this bit length function. So that's all for today. If you found this trick useful, please like the video, share the video with your friends, and also subscribe to the channel if you are new to the channel, and turn on the bell icon for more such programming related updates and notifications. Thank you one and all. Happy learning, happy coding.